use and interpret in a very, very friendly language. So the outcomes in this case would be, we will acquire the ability to apply quantitative research methods in solving real-world problems in various fields, including psychology, development, all that. We'll be using statistical packages to analyze large data sets, interpret results, report findings, and provide advisory where necessary. You could be working in an organization where people are not familiar with data analysis and interpretation. So in such circumstances, by the end of this class, you should be in a position to provide advisory. We will be in a position to incorporate quantitative methods in our research proposals. The last time we had a seminar, I gleaned that there is limited, if any, application of quantitative skills in most theses.
Hi, Joyce.
Please, Mulwa, mute.
Can we mute our mics if you're talking? Always the first thing you do is check your mic. But I'll have several co-hosts to support as Prof.
Thank you very much. Thank you very much. Materials that we will use in this class where necessary: reliable internet, which we are now using, e-learning platform, thanks to the School of Business, laptop and a desktop, mandatory. There will be e-journals in relation to some topics we will be going through. We'll share some journals which we have published, can interact with them. We'll have textbooks, real-world case studies and simulations, multimedia resources, and where necessary, LCD projectors. Now, these are the topics we are going to deal with. We did an overview last time and did some descriptive statistics. We are now going to, we also introduced analysis. So our package R, which most of us installed and at least ran some descriptive statistics. We are going to continue that. Data analysis is going to be part of this class from the beginning to the end. And this is going to be very friendly. We are going to learn introduction, probability theory. Most decisions we make on this planet are based on probability. We'll see how interesting probability is, discrete and continuous probability, or including estimation theory. We are really going to enjoy hypothesis testing. In the last seminar, I also realized or discovered that most theses are not aligned to hypothesis testing because most of them are qualitative and not mixed methods. We will enjoy hypothesis testing and give real-world examples. Then ANOVA. ANOVA is something we are going to deal with. and its application in the real world. We've done several papers in credible journals in ANOVA, which we will share. And we are going to enjoy ANOVA. We are not only going to calculate, we are going to run ANOVA using our software. It's very simple. ANOVA is applicable in development, in medicine, even in psychology. It's applicable everywhere. We are going to also look at the chi-square distribution and test, correlation and simple linear regression. We are also going to look at multiple linear regression, something that is very dear to most researchers. If you're using several variables and you want to see how they influence the outcome, where the outcome here is the dependent variable. We're going to run this using our software after understanding the concepts and the principles behind it. Then time series. Most people are not aware that past events influence present and future events. The same with data. So in this time series, we're going to see how, for example, if somebody is studying enrollment in education, you can trace enrollment from, let's say, when Kenya got independence, 1963, today, and that would help you forecast employment 30 years to come. It's a very important tool here that we're going to use. We are also going to run those R and spaces. When I discovered the model that has been used to predict COVID-19, I infused time series models that enabled predictions with a slew of other calculations, then had codes, created codes that would run it on our software. And that happened. I'm a big fan of time series. I actually also use time series models to create additional models for solving youth unemployment in low and medium income countries. Highly cited, around four models that created. Now, having said that, we have assignments here, assignment 1, group 1. We'll be weighting these percentages. We have assignment 2. And by the way, most of these assignments, the first 2 do not require any calculations. It might be just reasoning. Assignment 3 will be on ANOVA, using data that I will be providing in this class, at the end of this class. Then the next assignment, which also group, will be on multiple regression. Then the last, which would be individual, would require us to write a 1-page concept of quantitative research topic of your choice at the end of this. Now, this is the grading system. We value integrity. I'm just imagining that there would be no situation in which somebody gets E because of incomplete attendance, or withdrawal from class, or non-attendance, or any other. So your work in this class, should it be group or individual, must demonstrate originality, because that is when we are learning. We do not encourage plagiarism. And in all our writing styles, we will use the APA. In Africa, we haven't developed any writing style. So we're using the American Psychology Association style, APA. There are many styles, but academia in Kenya has chosen APA. Cheating in assignments will be penalized by failure of the assignment. Now, in the case of this class, previously I read somewhere that it would lead to disqualification. However, we have a redemption here. Given that now we also have psychologists here, you will be redeemed by redoing the assignment after 3 sessions of counseling. So the counselors in this class have work to do. At least they will have some work. But we pray that does not happen. Now, look at 5, point number 5. You are required to produce high quality work. Your writing must demonstrate scholastic rigor, signs of intelligent thought, creativity, and seamless flow of ideas. You must show conceptual clarity. I will also share with you some 2 published journals on what it takes to supervise a PhD, which I think a PhD student should be having that kind of information. Rigor in scholarship or scholastic approach to rigor means when you write something with clarity and something that somebody would read twice, because 1, they enjoy it, and 2, it is very thoughtful. When a researcher would read 4 papers to write a sentence, and they're all incorporated. Can you imagine reading 4 papers or 6 to write 1 sentence? It must be high quality sentence, that 1 sentence. You are required to read at your own time and read widely, because you like it or not, at this level, you are a scholar. And being a scholar means you read widely. There's no difference between he who does not read and he who cannot read. Presently, most people are very good at reading a certain book. It is called Facebook, but they don't read real books. So you'll be required to read widely. Now, attendance policy. All students must attend at least 70% of the course. I've read somewhere that it was required 75. We are alive to the fact that we are in various places and certain conveniences or inconveniences may warrant absenteeism, but not frequent absenteeism. Now, any learners who misses 30% of scheduled classes will receive grade A. Failure due to poor attendance, I hope that does not happen. This will be uploaded in the portal. Now, let me rush the class guidelines. 1, laptop and computer is mandatory. Laptop or desktop computer are mandatory in this course and during class sessions. As members of this class, we are together in this. We greatly embrace action learning and problem-based learning. We encourage active participation and interaction in orderly manner during and after live sessions. Every question counts and is treated with utmost urgency. Freedom of thought is valued here. Have patience and a sense of humor with technology. And let's have patience with each other as well. Keep an open mind when introduced to innovative ideas that may challenge your perceptions. Gladly, I request you, gladly challenge taken for granted assumptions. You might arrive at something that has eluded previous scholars. Because you are researchers and you are budding scholars. Be kind to everyone and never make any member of this class lose face. I've been in other forums where most people are intolerant. If somebody asks a question, there are giggles here, then no. Here, we are tolerant and we want everybody to feel valued in this class. So that is the coastline and our philosophy in this class. Now, there's a passage in the Bible that I value most. There's a passage in the Bible that we should, if you get your own time, you'll read it. It's about taking action. 2 Kings chapter 7, verses 3 to 20, talks about 4 lepers who, when the Assyrians went to besiege the city of Samaria, these 4 lepers were left outside. No supplies were allowed in to the city of Samaria, so there was starvation therein. But in the camp of Assyria, there was plenty. So without supplies getting in and out of Samaria, that was a crisis. Just like there was a crisis sometimes in Gaza when even supplies and humanitarian aid could not be allowed therein. But these 4 lepers reasoned this way. If we stay here, we will die of hunger. If we go to the camp of the Assyrians, they might kill us, we will still die. Or they might not kill us, we will not die. Either way, the odds of going are better than the odds of staying here. So why don't we just go? They took action. They went. But while they were going, the mighty Lord made the sounds of their feet be that of a mighty army coming. The Assyrians left everything there, running for their dear lives. These 4 lepers found gold and silver and diamond and food and horses, clothes, apparels, everything in plenty, just because they took action. So in this class, we take action. Now, let us now start learning.
Prof, I was just wondering, do we is there any reaction on the course outline, the assignments? If they would like to point out, I was just wondering, for example, one of the assignment requires a topic, and I know the question I've received in inbox is asking, now that we have a topic already, do we set another topic, or someone is asking in the inbox, is there a way of, because they're already having the topics moving on, is there a way they can keep moving and improving this particular class based on already what they are doing? E.g., for example, saying that can that topic be the same as the one in there? Can it be one that can improve, or can there be an alternative assignment that points towards like what they're already developing towards their topics that have already gone through? That's the question I'm receiving here. But again, they're asking whether they can have. I see Livingstone has a hand up. If he wants to ask the question, he can ask as well.
Okay, thank you very much, Daktari. That's an oversight on my side, and I apologize. I would require reactions to what we have said so far. Allow me to respond to that. If you have topics going on, and those that have been approved or have not been approved, in the course of this class, you may, the operative word here is may, find ways of including quantitative methods into that topic. I will be available for consultation. And then we look at design variables that are measurable and how to measure them, so that you can be in a position to include quantitative techniques in this. Now, any other question, please go ahead. Dr. You help me in that. Yes.
I think, Livingstone, you have a question, and as you come in, I think there is one that I've also received. In the spirit of tolerance on the issue of attendance, I'd like to request adjustments on Saturday classes. Most of us are facing challenges due to work commitments, church attendance, and open discussion around the possibility of earlier class, regardless of final decision. So I think there is also that, I think, not necessarily on directly, but I'm thinking maybe the question is more of whether starting early, maybe around, some people had suggested 7, people had suggested I don't know what time, but I think we were thinking this Prof, by Monday we'll have actually, is it by Tuesday we shall have actually given a way forward, and so that we can now, even crazy times are being suggested, so that 5:30, so that we can be able to agree. There could even be a possibility, who knows, that we could find a weekday in the normal weekday, the way the classes run in the evening. But I think there's a suggestion to have a meeting on Tuesday, so that we harmonize in the sense that even Professor Labanairo himself you know, and Professor Shem agree, like having 2 classes on Saturday following each other, that can be crazy. So we're looking at how best we can, of course, for Professor Euro, there are no assignments other than continue with your proposal writing and seminar writing activities. So they are not they're not very, very heavy as in terms of asking for assignments, but asking you to continue developing your proposal as you also learn on chapter 2, write up methods, chapter 3, and we move on. So I think that was the question, and they say that regardless of the foundation, go a long way in resolving the matter amicably and allowing us to get opportunity to be learning better. So I guess that time, that can be, you can also respond to it, but I have someone has a hand. I've already tried to respond in terms of that. We have a meeting on Tuesday, and we understand various religious sit-ups in the class. We also understand that if it means we compromise time, we can see whether we can begin a little bit earlier, like an hour earlier, or than 8 or so, or go to the 6 and then just finish at around 8:30, 9, so that you can be able to attend your daily activities for those going to service or those maybe around that. So allow us to meet on Tuesday to make this way forward, and I'm sure Prof and all of us will be telling you but if you have other suggestions, you can give to Prof. Livingstone?
Actually, that was my question. I look forward to Tuesday. Then we can see what has been decided. But generally, I live among SDS. I'm not one of them. And again, some work commitments. Like now, I'm very far away from Nairobi, so you find yourself working during a weekend. Kindly consider that.
Okay, I think Prof has had that, and he will also raise with different deans of this class, so that Tuesday meeting can be helpful, and we manage your best way. Maybe what would have helped us is, I wish the different groups can say, for example, if development studies could say, our day that dev students don't have a class for this cohort is maybe Monday, Tuesday, Wednesday, and then communication. We just need only 4 people to say these are the days that usually we don't have a class. Then that could also help inform whether we bring it back on a weekday. So if one person from dev can say these are the days, one person from psychology can say this is a day that we think can work, if it's Wednesday or if it is Tuesday. Another group from communication can say, I think if this class is considered for this day, it will work for our cohort. If you give us those, then we see that there is any day, if there's any day that literally ties, like now psychology says they don't have a class on Friday. And I know also development studies don't have a Friday. The question will be, is business and communication having a class on Friday? So that now, if business and communication say Friday is valuable, then we all go for Friday. I think development and psychology don't have a class on Friday. And then, of course, now we hear some of the business people don't have a class on Friday, meaning that we have a problem with some of the people in business and communications. But communication, if the dean or the coordinator can allow one class move another day and leave Friday, then that will really help, because already we have 50% of the class indicating Friday is okay.
Okay,
So,
thank you very much, Secretary.
yeah.
We acknowledge that we have a big class, and they are having different schedules, different activities, learning activities and work activities, and they are feeling mostly inconvenienced. We will build a consensus and find what works for majority, given that we are alive to the fact that we cannot have a 100% consensus where some people are not inconvenienced. But after Tuesday, we will communicate. There's a measure of inconvenience that we must all incur, so that we move forward. One last question, then we proceed.
Anything on the course outline you'd like Prof to consider? Let's leaving alone the logistics. Any question on the course outline? It will be shared on your WhatsApp as well, and your definitely your portal. So, but if you have any questions on the course outline, let us know. If not, then Prof will proceed on. I have the co-host helping on. It is getting to 1 a.m. here. So I will definitely take some rest, having worked the last 3 days, like almost on a 24-hour basis. So wish you well. And if you have any question, you can continue. Prof, I have some of the co-hosts here. They will help you. I'll make you the host. Once you've done the class, you can just end the class so that now the YouTube streaming can also end. Thank you.
Thank you very much for that sacrifice, Daktari. And enjoy the rest of your evening that side.
It's morning,
Okay.
actually.
Okay, morning. Okay, class, I want you to cheer up. This is not about mathematics. This is about you and learning. The last time you heard about probability, there were calculations that scared you. Now we are going to give a human face to probability in a manner that we can feel, we can interact with it. So here is a story on uncertainty, a very small one. And I want you to be very attentive. A lawyer, an economist, and a statistician were holidaying in Lucania. Glancing from a van window, they observed a black sheep in the middle of the field. How interesting, observed the lawyer. All sheep in Lucania are black. To which the economist responded, some sheep in Lucania are black. The statistician gazed heavenward in supplication and intoned, no. In Lucania, there exists at least one field containing at least one sheep, at least one side of which is black. What do you make of that statement? I want somebody to say something around it. What do you make out of that short excerpt? Yes, Rachel?
The statistician is not making assumption. It's just being is observing like what is there without making assumptions. So by saying there exists one field is because he has just seen that field and he has just seen the sheep, not knowing the other side, whether it's black or white. So the statistician is not making any assumption. He's being realistic.
Please clap for Rachel. That's very, very accurate answer. Whereas others are relying on generalities. The lawyer says, all sheep are black here. The economist said, some of them are black. But the statistician is saying, no. We have only seen one field. There could be other fields. We have only seen one sheep in one field. There could be other sheep elsewhere here in Lucania. And if anything, we have only seen one side of that sheep. The other side could be white or any other color. Now, that is a strong implication of probability. That there's a probability there are other fields in Lucania. There is also a probability that there are other sheep in those other fields. And there's a probability that this one sheep we have seen, the other side we are not seeing could be white. it's all to do with the training all these people have had. Whereas there is large generalization in law, there is some level of generalization in economics, but there is very little generalization in statistics. Now, that is how we approach statistics here. We give it a human face. We talk about daily things that happen. Now, if you look at the introduction of probability, probability is the likelihood, the measure of likelihood some an event will occur, may or may not, just the likelihood. We're dealing with the likelihood. And we know that probability ranges from a scale of 0 to 1. So between 0 and 1, there are asymptotically many values. Could 0.001, there are too many. When between a space of numbers there are too many other values, we say quantitatively we say they are asymptotically many. Now, if there's a probability of 0, the event is unlikely to occur. And those probabilities are very limited where we have a probability of 0. But when there is a probability of 1, we are almost certain that the event will occur. For example, there's a probability of almost 1 that every day the sun will arise and set. But there's very 0 probability that the sun will now begin rotating from west to east instead of east to west. So between 0 and 1 expresses the likelihood of an event occurring. So every time we talk about probability, think of chances that something will happen or will not happen. An event will occur or will not occur. So what are the reasons for probability? Why is probability important? We have situations that we need to know, or at least assign some value that this thing is going to go this way. For example, the two events that we've talked about, the sun rising and the sun rotating in the reverse direction, those are known. We don't need probability for that. But if we have in daily life many factors that contribute to the occurrence of an event or a situation, we need to assign probability. So that's why we say in life situation, most things or events are stochastic. Stochastic means probabilistic. There are chances that they will occur or will not occur. That is the meaning of the word stochastic in statistics. Sometimes we need to make a decision. Given several options, we evaluate all the factors supporting the occurrence of this option, and then look at the other side and make our own decision. So in such situations, we assign probability. Then there are counting techniques. For example, now when you are in research, like all of us now in research, we have the sample space. Sample space is the number of possibilities. If you're talking about a hospital, or let's say a class, like in this class, if we have reached 60 and we wanted to have a sample of 30, our sample space is 60. Now, if you must take 30% of that, that ensures counting. And that 30% is also probability of 0.3. So the techniques that are used in this course, we have probability tree, which we all learned in high school. Then we have permutations, which I presume some of us learned in high school, and combinations. A probability tree is decision, sometimes people call it decision tree. It is called a decision tree because let's say you have two children and they both have probability of passing examination, and then you take them to high school, they still have probability of proceeding to the university. So at each point from the start, you decide based on their performance and given the resource constraint, who should go first? Or where should the other one go? That is probability tree. I will show that kind of a tree later on. Now, in a probability tree, it's a graphical representation of events and decisions to be made. However, when the numbers of decisions to be made are too large, we may not use probability tree. An example here, a bag contains 4 red and 6 blue balls. Then 2 balls are drawn at random without replacement. Now, when we talk about probability and drawing of balls or coins without replacement, if you had 10 balls in this case, then you pick 1 red ball without replacement, it means what remain there are 9 balls. Now, we can use a probability tree to see the possibility, the probability of choosing 2 red balls. I'll show that in a diagram. And the probability of choosing first red, the second blue, probability of choosing the second red and the third blue. let's take, for example, in a situation where people are in a democratic situation where people are maybe taking a vote to make a certain decision. It could be a gender decision. And there are females and males here. And one would have some idea of how many, the likelihood to vote for this decision or not to vote for this decision. That lies also in the dichotomy, male and female. That fits so well in a decision tree. So at the beginning, if you see my cursor, this is the first divergence. They are 10 balls, 4 red, 6 blue. You are here. So the first decision are 4 balls. The next are 6. So there are 4 over 10, because 4 plus 6 is 10. Those are red. Then there are 6 over 10. Those are blue. So if you choose the first red without replacement, they are here. It is 4 over 10. 4 over 10. However, if you choose the second red without replacement, it is 3 over 9 because you have removed 1 and you have not replaced. So how do you know that probability? It is the probability of the first decision times the probability of the second decision, which is 4 over 10 times 3 over 10. Those are 12. However, if you choose the first is red, the second is blue. So the first decision is 4 over 10. Blue in this case is 6 over 9, because the first time you're choosing it, the number was still 6. Now, if you multiply 4 over 10 times 6 over 9, using your calculator, what do you get? Now that we have scientific calculators, it is 4 times 6, which is 24, over 9 times 10 times 9, which is 90. So that is 24 over 90.
4 over 30.
Sorry, could you please just go back a little bit?
Okay.
I got the one on the 4 over 10 times 3 over 9, which is 12 over 90, but I missed the second bit.
Okay, the second bit being, if your first choice or decision was to pick a red ball, and then you pick a blue ball. Red ball here is 4 over 10, but you've removed 1. So the number remaining in the basket are 9. Now choosing blue ball, 6 over 9, because you had never chosen blue before. So you multiply 4 over 10 times 6 over 9. You get your answer.
Why does the 6 become 6 over 9 when you've chosen the blue? Like when we're choosing the red, we choose the first red, which was 4 over 10, so it became 3 over 9. So if you pick the next blue, which is 6 over 10, then it should then be 5 over 9, in my understanding.
We had never chosen the red blue before. In this decision, you look at, we have taken the strand on the red, the branch of the tree on the red. We chose for one red ball. Out of 10, we chose one red ball. Now, after choosing one red, the next choice you make will be out of 9 because you have removed one ball already. So we removed one red, so we remain with 9. But you have not removed any blue. So all the blues are remaining over 9. So you choose, it will be 6 over 9. If you multiply those probabilities, you will get 24 over 90, which you can simplify. What does it come to?
Prof, I think we are a bit lost. We were dealing with the red. When did we start blue again?
Yes, that is why it's called a decision tree. We have a basket. In this basket, there are 4 red balls and 6 blue balls. So if you see my cursor, you either choose the red this side or the blue this side. But you first decided that, I'm choosing the first red. Then you choose first red. Now, out of those 10 balls, you have taken one red. Then you have put that one red separate. Still on the same side, you decided to take another one blue. Now you're choosing out of 9 because you had already removed one from the 10. So you're removing the second from the 10. So this second from the 9, you're removing one from the 9. See, you started from here. Out of the 10, there were 4. 4 red, you chose one. So it was 4 over 10. Then when you reached here at this joint, you decided, I don't want to pick another red. Now I want to pick another blue. What is the probability of getting one blue? There are 9 balls remaining in the bag, but I have to pick one. But all of the 6 are blue. So the first one, I'll have 6 chances out of 9 of picking a blue ball. If you do so, you'll get 24 over 90. Now, suppose you decided to pick, your first was blue. The balls are 10. So the first is blue. You decided to choose blue. So there are 6. So it is 6. The chances you have here are 6 over 10.
Sorry, Daktari.
Yes, please.
I'm getting you on the one of the 9.
Yes, yes.
And on the one on the 9, I'm getting you very well.
Yes, yes,
The
yes.
challenge I'm facing
Yes, yes.
is that for the red balls,
Yes, yes, yes.
when you picked one,
Mm-hmm.
it reduced to 3.
Yes.
But when you choose the blue,
Mm.
I understand that the balls now are 9.
Yes.
Why isn't the blue reducing to 5?
In the first case, we chose 2 red balls. The question here, find the probability that drawn balls are 2 reds. So for you to choose red, this is the first red. Out of 10, there are 4. So your chances here is 4 over 10. Now you have removed that red. You are picking the next red. The balls have remained 9. But You have removed 1, so there are 3 balls out of 9. So if you pick it, it is 3/9. These are 2 reds. In this case, the second case, you have chosen the first red, 1 red, and 1 blue. Red chances of picking the first red are 4/10. So you remove that 1 red. You remain with 9. But the chances of picking a blue, because you've not removed any blue, are 6/9. That's how 6/9 comes here. That's why if you look at the second branch, the blue branch down here, if you see my cursor, the first, if you draw 2 blues, the first blue is 6/10. You remove that one. The next blue will be 5/10. If there was going to be a 4th blue, it will be 4/8. However, if on this branch, we decided that our first was going to be blue, our next was going to be red, we're just picking 2 balls. The first blue, you have 6 balls out of 10 in that bag. You pick the first, you have 6/10 chances. Then the next one, you pick the red. Red are still 4. You only removed 1 blue ball. So it'll still be 4/9. That is the decision tree as it is made. Now, this is without replacement. You choose, but you don't replace. I do not know if that is clear enough. In case it is not, we can interact with the problem individually in consultation. But once you have this,
that's okay. We'll catch up by and by.
Okay, thank you very much. Now here is when you replace, you pick and replace. A bag contains 12 balls. 3 are red, 9 are blue. So 9 plus 3 are 12. So in our bag, we have 12 balls, of which 3 are red, 9 are blue. Then a ball is drawn at random. See, I really like the way people use the word of random these days on the street. That I randomly saw him. That is not random. You chose to see this person. Random, like when you are blindfolded, then you are given balls, or you are put in a group of people. So you try to group and find one. That is random, at least statistically. So in this case, in this bag, you choose at random and replace in the bag. So when you pick one from the bag, you don't remove it, you replace it and pick another. That is what we call without replacement. In without replacement, the denominator does not change. Like the chances of choosing 2 red balls here, the reds are 3/12, 3 in a bag of 12. You pick one and return it. That's the first event. The next event, which is here, you pick one and return it. So the probability of choosing 2 red balls with replacement is 3/12 times 3/12, which is 9/44. If you simplify, it's 1/16. Now, the chances of picking the first red with replacement, and then the next pick is blue with replacement, you follow this path, 3/12. Then you come here, you don't go to the red, you come to the blue, 8/12. 3/12 times 8/12 is 24/144. That looks like 1/12. So one thing we learn here is that when we replace, the denominator does not change. It remains 12. But
I have a question.
Please go ahead. Go ahead, Jessica.
Because you're saying if I pick a red, 3/12, yeah. I've replaced the red or the one that I've picked. So
Yes.
the denominator remains 12. However, when I pick blue,
yes.
I thought in the first one it should be still 9/12. Because you didn't pick blue and you've replaced. So how comes it goes to 8 and not 9?
Yes, you are right.
Yeah.
There you are right. Thank you for that. You're right. Because we are not replaced, we are not picked any blue at all. Thank you for that. This figure here should be 9. If you choose 2 blues, the first is blue, the second is blue, it's 9/12 times 9/12, that is 81/144. Now we are going to talk about permutations. You will interact with the notes on probability decision tree at our own time. Now let us talk about permutations. I want to tell you a story. During World War II, 1939 to 1945, Germany, Italy, and Japan was on one axis. Then there were other allied forces, including the US, the UK, and others. Now, in war, sending information has to be as discreet as possible. And you do not want the enemy to discover or to make out the information you are relaying. That time, they were using telegraph. Then the Germans came up with a machine called Enigma machine. This Enigma had several sections. Letter A could be written in several other ways. When fractured on the other side, it can be letter B. But then the person who has sent you that message sends you another note on how to arrange those numbers. So there were U-boats that they were used to sink other ships. There are also missiles. They were shooting planes, bringing down warplanes and warships. Now the Allied forces could not find how to decode the codes put in the Enigma machine. And that was a lot of trouble. No mathematician could help. Then came one person. His name is called Alan Turing. Alan Turing used permutation. He designed his own computer, his own computer, or the first kind of machine that could scramble numbers and crunch them. But every time the Allied forces, every time the Germans realized there was some detection, they altered the Enigma machine. And this troubled scientists. It was Alan Turing who helped the Allied forces using permutation to scramble the codes that the Germans were sending to sink the ships and then bring down warplanes or bomb other places. And that was the first time permutation was used to solve a real human problem. This Alan Turing, if I were to tell you further, went ahead and developed the first computer. It was almost as big as our whole room. And because the British knew that he had too much information, too much secrets on the British information, this guy was kind of hounded. He finally died. And they said that it was out of suicide. Cyanide and a beaten apple was found in his room where he was staying. And they said that the cyanide, the apple was laced with cyanide. And that is how he died. So I want to tell you that it's not a coincidence that the mighty Apple company chose a beaten apple as their logo. This is traced back to the tragedy that befell Alan Turing after the World War II, when some people postulate that it is this government that eliminated him because he had too much information, knew too much about the British Army secrets. So you see, knowing too much can also kill you where the government is concerned. And most scientists have suffered that way. It was not Alan Turing who died. This starts all the way from Galileo. So every time you buy an Apple machine, Apple phone, iPhone, or whichever one, remember Alan Turing. He beat an apple that was later said to be laced with cyanide. So there's a brief story about permutations. Now, in permutation, it is about the order of arrangement of numbers. For those people who are doing coding, you know that 0, 1 is not the same as 1, 0. They're not synonymous. So we're saying in permutation, AB is not the same as BA. AB is not the same as BA. So the idea is on the arrangement, not on the number of in which this can be arranged. So if you are given two letters A and B, they can be arranged in two ways, AB and BA. So in permutation, we are saying there are two different arrangements of the same letters, where N, the number of distinct objects which are ordered, which an ordered arrangement is to made, and R, the number of objects in the arrangement. this should be done practically. So when we say concept of factorial, if we say 6 factorial, because factorial is part of arrangement. If we say 6 factorial, it only means 6 times 5 times 4 times 3 times 2 times 1. You multiply the numbers that are preceding 6. So in a factorial, if you are asked all the ways in which ABC can be arranged, it can be arranged 6 times. So 3 factorial is 6, because 3 times 2 times 1, that is 6. So ABC can be arranged ABC, ACB, BCA, BAC, CBA, CAB. There should be 6, not 5. So in permutation, we use factorial. So this is denoted by n permutation R. It's the total number of objects, but you want to pick a certain number and then arrange the rest. So it's given by n factorial over n minus r factorial. So if we talk about example 6 permutation 3, it means our n here, n factorial is 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, giving us 720, over 6 minus 3 factorial. 6 minus 3 is 3. So 3 factorial is 3 times 2 times 1, which should give us 6. So 720 over 6 gives us 120. So our combination here is 6 combination 3. I've been nursing an idea of a research idea. This is a mathematical research idea where we would find a solution to universities, colleges, what and what, having not to worry about timetables. If it is in a school, you have, let's say, 12 teachers, and you have 7 subjects or 10 subjects to be taught. How you can feed that into a combination and know the total number of lessons that should be have in that semester, and go ahead to design a code, an AI code that would actually put the names of the teachers and the times of the location of the lessons and produce an Excel sheet that would work with that. That would be one application of permutations. So anybody with a question on permutations, ranging from Alan Turing to where we have reached from the apple which we use without knowing the sacrifices other people made?
Mwalimu, yes, I have a question.
Please go ahead.
The narrative part is, of course, extremely excellent.
Yes.
I wish it would just reach there. But now that it has to, now that it has to go,
Yes.
Beyond that. Just a moment, Mwalimu. Just a moment.
Okay. So you all see that.
Sorry, Mwalimu, I was getting a bit of interruption.
Go ahead. Go ahead.
Yes. I was just saying.
Yes.
Unfortunately, I wish I'd not done law, but law creates a mind that seeks logic. So
yes, yes.
I keep asking, I keep looking for logic. So when you say the permutation of any,
yes. Mm-hmm.
Pardon?
Mathematics is equally logics. Go ahead.
Yeah, but in a stranger way, yeah. So when you it's a stranger way than law, for instance. So when you say the permutation of any object taken at a time is denoted n. What is this n? Where did n come from? Why not q?
N is the total number of objects. Like if you go.
So where the objects here would be like the ABC. So the total number of objects would be like
yes,
ABC.
yes.
So it would be like 3, yeah?
Yes.
Okay. Then what is R?
So R are the number that the object we've selected out of those n.
Mm-hmm.
Yeah, like in this case, example here, 6 permutation 3. Our n here is 6. Our R is 3. So n minus R.
Mwalimu, sorry, but how is our n 6 and there's only ABC? So our n should be 3.
We have taken a situation where our n is 6, permutation 6, where we have the first example.
Oh, okay.
You use the first where we permutate factorial 6. If we were to use 3 and say that 3 permutation 6, 3, it would be 3 p then 2. Instead of 6 p and 3, it should be 3 p and 2. Where in this case, it should be n permutation, that would be 3, n factorial to 3 factorial over n minus r. Our r was 2. 3 minus 2, also factorial. Now factorial means 3 times the numbers that precede it. So 3 times 2 times 1. But 3 minus 2 is 1 factorial. 1 factorial is just 1. So we have 6 over 1. The number is 6. So 3 permutation 2 equals to 6. Now 6 permutation 3 means 6 factorial over 6 minus 3. Our r here is 3. Our n here is 6. And the numbers that precede 6 are 4, 5, 3, 2, 1. The numbers that precede 3 are 3, 2, 1. So n permutation 3, 6 permutations 3 can be 120 different arrangements. If you take any 3 objects out of 6 and you want to arrange them in different ways, you'll arrange them 120 times. Now you can see the problem that Alan Turing had with the Enigma machine of the Germans, that a simple word, let us 6, could be arranged 120 times. So suppose it was 12. And these numbers were enormous at that time. So that is permutations. Now we have combinations. Now, the difference between permutation and combination is the absence of order, where combination is an arrangement of objects without regard to order. E.g., AB and BA are considered to be the same. However, in permutation, AB and BA are not the same. But in combination, they're the same. Now, given N, which is the number of objects, and R, which are the set of objects under N. Out of N, let's say out of N are 10 or 6, we have used 6, then R are 3. Then to find a combination of N combination R means 6 combination 3. The formula is a bit different in that we just insert R factorial followed by everything else remain the same in the denominator. Whereas in permutation, there's no R here if you're seeing my cursor, but in combination, that R is there. So let us get an example where 3 combination 3. Suppose a committee of 3 people is to be formed from a list of 3 members of this RS851 class, ABC. If any of the 3 can be arranged, seated in any way in the committee, how many ways can the committee be formed? We only have 3. Now we have to seat them. In how many ways can the committee be formed? There are only 3. Just 3 combination 3. So 3 combination 3, using the formula here, our R is 3 and our N is 3. So this is the same as 3 times the numbers that precede it over 3 times the numbers that precede it into bracket into 3 minus 3. The answer becomes 1. Now suppose it is 3 combination 2. If you have where you can write, just write 3 combination 2 equal to 3 combination 2, the same way you have written 3 combination 3. This is the same as with n factorial, just n over r factorial, n minus r, out of bracket factorial. This is the same as 3 factorial over 3 factorial, over 2 factorial, sorry, over 2 factorial over 3 minus 2, outside bracket factorial, which is the same as 3 times 2 times 1.
Excuse me, Mwalimu.
Go ahead.
Are you working out somewhere?
I'm asking you to work out something, and I'm working it on my own.
Okay.
Using this formula, can you do 3 combination 2?
Okay.
It is 3 combination 2. Our R is 2. Our N is 3.
Prof, just to take you back a bit.
Yes, please, Collins.
3 combination 3. How are you coming up with the 1? Because 3 minus 3, that will be 0. Then 0 in bracket times 3. 3 by 0, we get 0. So 3 divided by 0, how does it give us 1?
The first, it is R factorial. And N minus R factorial. The R factorial here does not affect R factorial, N minus R factorial here. Because if you have 3 people and you have to form a committee of 3 combination 3, and they have been seated, there can only be one way in which they can be formed. Now look at how we are going to treat the 2. 3 combination 2. Try the same method and see what you get.
I think, sir, he's saying that when you do 3 minus 3 is 0. 0 factorial is 1. So he's thinking that 3 minus 3, 0 factorial is 0. 0 times 3 factorial is 0. When you divide something by 0, it's math error. So it's 0 factorial, which is equal to 1.
Okay.
So that is his confusion, looks like. Maybe he can
Thank you, sir.
clarify.
Thank you, sir. In your scientific calculator that you have there before you, there is combination. If you look at the first button is shift. The next button is alpha. Below alpha is N combination R, NCR. Are you seeing it? So you press 3, then press NCR in your calculator, 3. That is 3 combination 3 equals to 1. It will give you that. You can also try that with 2. 3 combination 2, you will see. Yes, Collins, your answer is equally correct. Because 0 factorial, 1 factorial is 1. So either way, we are getting 1. So now, use your calculator to get 3 combination 2. Has anybody obtained it? Or we don't have calculators yet? If you don't have, we're calculating it manually. To calculate it manually, n factorial, our n is 3. The formula is n combination r equals to n factorial over r factorial into n minus r factorial. Now, if you know that our n equals to 3 and our r equals to 2, use that formula and get the answer.
So the answer I'm getting for that is 3.
Wonderful. Yes, that is 3.
I got 3.
Yes, the answer is 3. So you see how scientific calculator is helping this be done easily. This is also work of Alan Turing. So with your calculator, you can actually calculate 9 combination 4.
Just a second, Prof.
Go ahead, Caroline.
So I think the second explanation makes a lot of sense, because if you do 3 factorial over 2 factorial into bracket 3 minus 1, you actually get 3, both manual and by using the calculator. The first one still doesn't make sense because of the 0 thing. I don't think you've explained very clearly for me to understand how 0 equals 1 in a combination calculation.
So 3 factorial.
3 combination 3. That's where the confusion. I'm getting confused.
Combination 3.
Yes.
So let us calculate it. Anybody can be wrong here.
Yes.
Yes. So let us first calculate it manually, okay? Then
Sir, for the benefit of others, is it possible you can use whiteboard and write it there so we can all follow? Thank you.
I haven't used whiteboard in this class or in other class before. I will need help on that. If I calculate this thing, it brings 1. If you can combine that in your calculator, it also brings 1. Now, if you look at the factorial, the reason why it brings 1 is this, Caroline. There is the r factorial. The r factorial, r and 3 are the same here. You have 3 and 3 combination. But the 0 inside the bracket, if we multiply the denominator and get 0, but n factorial over 0 is infinity. Is that so?
That's true.
3 over 0 is infinity.
Yes.
Yes.
And does infinity equal 1?
No.
So why is our answer 1?
Our answer is 1 because it's the least combination possible here. I think what they have also factored in the calculator.
Prof, can I just
make
break
a suggestion
down something?
Yes, please. Yes.
So if we work with 3 combination 3, using the formula provided, we'll have 3 factorial over 3 factorial, then bracket 3 minus 3 factorial. So 3 minus 3 will give us 0. So the answer we'll have for that is 3 factorial
over 3 factorial.
Over 3 factorial and 0 factorial. So 3 factorial is equal to 6 using the formula or whatever we did previously. 3 factorial is, and 0 factorial is 1. So that will give us 6 over 6. We can use decimal.
Times 1.
Yeah, we can also replace it with multiplication sign. So basically we'll have 6 over 6 times 1. And then
over
that
6.
Will give us 6 over 6.
Yes.
6 over 6 is equal to 1.
Yes, this is true. This is very true mathematically.
I think for the benefit of many in the class, I think the most important understanding here is the fact that the factorial that comes after the bracket. So a 0 factorial is the least minimum number available, which is 1. I think that's where we're getting confused.
Yes, because the minimal number of factorial is 1, which is 0.
Do we still have that infinity argument then? It's not there, right?
No, we don't have infinity argument because now we've factored 0.
Awesome.
Now, the easiest way when you are given a factorial, when you want to factor things, for example, if it is 17 factorial, in combination 10. If you use a scientific calculator, that will be 448 ways of arranging 10 objects out of 17 without order. So somebody might ask, how might this help us practically? What is the practical application of this? Who can see possibilities? Other than what Alan Turing has done or did, and his tragic end, we can use this in assigning, in coding. You see, mostly again in war. Or in any other distribution where you have to assign objects to certain places at the same time. You can code. For example, 0 and 1 can be coded, can mean 2. It can be coded twice, 0 and 1, 1 and 0. We can also do further research and use this in informing, assigning timetable and facilitators. I would have gone to another one. So we have done this combination. So another example of combination is a list of 5 groups are to eat at a funeral in their constituency. In how many ways can we arrange the groups with 3 eating in the tent? The first group, A, are in-laws. O are the church. M are politicians. B are visitors from Nairobi, as always. And P are friends. Now, these are 5 groups, but we have a tent. we have to make them fit 3 of the 3 in of the people here to fit in the tent. We have 3, 3, 3 out of the 5 groups to fit in the tent to eat. So we find in how many ways we can combine all these people to eat. And maybe the people from Nairobi do not want to mix with the in-laws. So permutations enables us to do. That is 5 combination 3. Now, can somebody find that using your calculator first? 5 combination 3. These are situations that we have on daily basis. Now, the answer is here. I want to see if anybody has used the calculator to calculate this. By show of hands. Thank you, Mula. Thank you, Kawira. Thank you, Rachel. So next time you have a meeting where there are in-laws, there's church, there's the leadership, there's the visitors from Nairobi and friends, you can use a combination. Now, to demonstrate this, they can be out of AOMP BP, we can have arrangement of AOM, AOB, AOP, AMB, AMP, ABP, AMB, AMP, OBP, MPB. Those are different arrangements in which we can arrange those groups. So in probability, we have experiments, outcomes, and events. Where experiment is a process which results in a number of possible outcomes, and the possible outcomes are known beforehand. But one cannot say with certainty which outcome will happen. For example, if you're given a fair coin to toss, you realize that when we have to use the word fair so that the results are neutral. When you toss it, you cannot predict. There are equal chance of occurring. Or if you roll dice, 6 faced dice, the chances are known, but no, you can't know the material outcome. Now, when it comes to a coin, a fair coin, the sample space is only 2. It's either head or a tail. But you cannot get a head and a tail at the same time because they are mutually exclusive. The chances of one occurring negates the chances of the other event occurring. So if you're given a fair coin, an experiment, you toss the coin. If you get a head, you're not going to get a tail unless you throw it twice, which you might also have 2 heads instead of a head and a tail, or 2 tails, either way. So all the possible outcomes are what we call the sample outcome. Yeah, if you throw a fair coin twice, the sample space are only two, head or a tail. However, if you throw it twice, you can have head, head, you can have tail, tail, you can have head, tail, and tail, head. So the possibility, the sample space here would only be 4 if you toss it twice. But it is some kind of arithmetic progression, because if you throw it 3 times, it increases by a power of 2. I did not want to bring that into discussion here because this is not pure mathematics, this is statistics. So let us look at types of events in probability. We say an event or two events are mutually exclusive if the occurrence of one negates the occurrence of the other. Like what we've seen in a coin. If you toss it, once you have the head, you can't have the tail. When we say we have collectively exhaustive events, it means the events include all possible outcomes. Like the exhaustive events in tossing a coin are head and a tail if you throw it once. If you toss it twice, the exhaustive events are 4. Head, head, tail, tail, head, tail, tail, head. Independent events, where the occurrence of one does not affect the occurrence of the other. Independent events is when the occurrence of one event does not negate the occurrence of another. For example, it can be cloudy and windy. It can be sunny and windy. The presence of sun does not negate the absence of wind. But dependent event, dependent events, if the probability of occurrence of one is affected by the occurrence of the other. For example, rains and floods. It's not going to be flooding without rains. It's not going to be cloudy and sunny at the same time. Those are dependent events. Can we take a brief break? Let's say 10 minutes break and then resume. Only 10 minutes break. Now we are back. Yes, Ken Williams, please mute. We have something we didn't do last time. We did not install, some people had problems in accessing and using the R software we introduced in class. So I would want us to conclude with probability. Then we touch briefly on that R, because we are going to use it every other time, especially now in the next lessons going forward. So we talk about the last part of this is conditional probability. This is a probability that depends on the occurrence of another event. The probability are conditional. In this case, one event necessitates the occurrence of another event. That is what we call conditional probability. It is written as, for example, when event A, the likelihood event A happening, given that event B has already happened, can be denoted as probability of event A happening, PA/B. That is probability of event A happening given that B has happened. So if you know the probability of B, you can get the probability of A. Now, for example, consumption of alcohol and liver cirrhosis, or smoking and lung cancer, those are conditional probabilities in that situation. So when we talk about conditional probability, look at it that way, that in event A will only occur given that event B has occurred. The likelihood of having lung cancer when you're not smoking is less than having lung cancer when you're smoking. The likelihood of having liver disease when you're not, when you are teetotaler is less than when you are alcoholic. So that brings us to these laws of probability. Then now we will deal with the conditional probability. Let us first deal with the laws. We have additive law. When events are mutually exclusive, and the probability of them happening is in additive law. You add them. For example, if you toss a coin and you want to find the probability that either a head or a tail is the outcome, you add the probability of a tail plus the probability of a head, which in this case is 0.5 and 0.5, a half plus a half, which is 1. This applies to mostly mutually exclusive events. Another example, example 2. In Naivasha KCB Kenya Rally 2026, the probability of cars winning A. Peugeot, B. Toyota, C. Ferrari, D. Subaru are a half, a fifth, a sixth, and a seventh, respectively. Now find the probability that one of the cars will win the rally. You just add them, one of the car.
Did you create those fractions? They're determined by something.
The only determining factor here is that one, these are the most common cars locally. Two, I might be wrong, but some of them are some of the most speediest cars that we have around. So as of now, let us just treat the probabilities assigned here, these fractions, as arbitrary.
Excuse me, Prof. Where are you getting the denominators 4, 5, 6, 7?
If you assign, we have said these are arbitrary probabilities. I have decided to assign Peugeot 0.25 chance of winning. That's a quarter. The Toyota, a fifth chance of winning probability. These are arbitrary. This is no way in relation to the performance of the cars in question. These are arbitrary for just class learning purposes. I am afraid if your car brand is found here, it was not intended that way. On a lighter note, it's only for the purposes of learning. But now, given these assigning probabilities assigned here, the probability of any of the cars winning, that is under additive law, you just add their probabilities, and that would be the answer. However, okay, go ahead, Hussein.
Sorry. In addition, are we adding and the way they come first? First vehicle 1/4, second vehicle 1/5. Is that the way they increase it? Sorry.
No, you can add them in any other way, you still get the same answer.
Thank you.
Thank you very much. Now, however, for exclusive events, the probability of them occurring together is 0. For example, when you toss a coin, you cannot have both head and tail occurring together. No. And coins barely land on the third face, where the third face is that small space that are surrounded, that circumference. They barely land that way. So either way, you cannot have both head and tail. Now, general additive law is that we have said that for mutually exclusive events, we add their probabilities. However, in this case, we are having a situation for events which are not mutually exclusive. The probability that one of them will occur is determined as follows. Probability of either A or B occurring is given by probability of A occurring plus probability of B occurring minus probability of AB occurring at the same time. And there is an illustration, an example here, that suppose 80% of tourists who visit Kenya visit Nairobi, 70% visit Mombasa, and 60% visit both Nairobi and Mombasa. What is the probability that a tourist coming to Kenya will visit at least one of the two towns, one of the two cities? So the probability that the tourists will visit Nairobi is 80%. When you express this into probability, it is 0.8. That if you visit Kenya, you will visit Nairobi. In fact, most of the time, the international flights land in Kenya. There are also international flights that land in Mombasa. Then there are also international flights that land in Eldoret and Kisumu. For the purposes of this example, we just chose the two major cities in Kenya. Now, if a tourist comes to Kenya, then the probability that he visits Nairobi is 0.8, and the probability that they visit Mombasa is 0.7, and the probability that they visit both towns is 0.6. Now, for us to find the probability that they visit at least one of the towns, at least once, one, the probability is given by probability of visiting Nairobi plus probability of visiting Mombasa minus probability of visiting both Nairobi and Mombasa at the same time, which in this case is 0.8 plus 0.7 Mombasa minus 0.6. The answer comes to 0.8, the 90% chance that they'll visit either of the cities. That is the caveat of that additive law. Why would it be so that we subtract the probability of visiting both Mombasa and Nairobi? The trick is in the at least. Then we have the multiplicative law, which we did up there when we were looking at the decision tree. If events A and B are independent, the probability that both A and B would occur is a product of their probabilities. So probability of A and B occurring is probability of A occurring times probability of B occurring. An example is given here. A person can hit a target 4 times in 5 shots. Another person can hit 3 times in 4 shots. And person C 2 times in 3 shots. Calculate the probability that person A, B, and C will hit the target. You multiply their probabilities. Person A, B, C hitting the target is probability A times probability B times probability C, which in our case here, if we express them in terms of fractions, A is 2 out of 5 times 3 out of 4 times 2 out of 3, which in this case comes to 2 out of 5, that's 0.4. If you calculate the probability of B and C hitting the target and A missing, you get the probability as indicated here. That goes for the probability of A and C hitting the target, but B missing the target. We are going to also look at the general multiplicative law. For joint events, dependent events, the joint probability is computed as probability A and B jointly occurring is given as probability A times probability B stroke A occurring at the same time. Now, that would appear strange until we look at the example and how it is computed. For instance, in a competitive exam, 30 candidates are to be selected. In all, 600 candidates who will apply for the exam, only 100 will be shortlisted for the interview. What is the probability of a person being shortlisted and getting selected? So out of 600 candidates, 100 are to be shortlisted. And out of those shortlisted, 30 are to be selected. What is the probability of being shortlisted and getting selected? So you see, the probability of being shortlisted, since 100 are being shortlisted, that is 100 over 600 here. Then the probability of being selected is 30 out of those 100 shortlisted. So it is 100 probability of being shortlisted, 100 over 600, times probability of being selected after being shortlisted, which is 30 over 100. If you multiply them under multiplicative law, get 0.05. which is a very realistic figure today in Kenya, given the unemployment rate. I'm glad some of us here are tackling unemployment in their research work. Now, there is a gentleman. This gentleman is called Bae. Bae had his theorem in 1763 on conditional probability. For those who are doing economics, you know Bayesian economics. What happened is that this Bae in 1763 was intrigued with the decision tree and wanted to come up with an irrevocable theory that is assigned to conditional probability. He wrote his manuscripts, did his work excellently, wrote his manuscripts. However, before he could publish them, he died. He went to meet his maker. Now, his family kept his manuscripts until 1773, 10 years later, and gave Thomas Bae's manuscripts to Price. Price looked at the manuscript and found them good, and they had some editing that needed to be done, very substantial work. Price did very enormous work with them. Just to avoid plagiarism, he decided to attribute all that work to Bae. Where some scholars in the probability theory said that it should have been Bae and Price. But Bae, being a consummate statistician at that end, gave all credit. Now, Price gave all credits to Bae. It is from Bae that we now have conditional probability. This is the probability of event A occurring, given that we know the probability of event B occurring. It is computed as follows. Probability of event A occurring given B has occurred equals to probability of B given A has occurred times probability of A occurring over probability of B. So probability of A stroke B is probability of A given B has occurred, probability of B given A has occurred, and then probability A, probability B are individual probabilities. If today Price had to do the work and to edit the work that Bae did, it would have been a different story. It would have been Price theorem or Price-Bae theorem. It would have been just Bae's theorem. So we have an example here. And this would really interest the economists in this class, especially health economists. In a clinic, patients claiming to be having liver disease are presumed to be alcoholic. Past data show that 10% of patients entering the clinic have liver disease. The probability that a patient is alcoholic is 5%. The probability that patients diagnosed with liver disease are alcoholic, 7%. Now, find the probability that the patient has liver disease given that he or she is alcoholic. In this case, if you go back to this formula, probability of A given B, which is what we are looking at, probability of having a liver disease and is alcoholic, we assign values as follows. Probability of a patient has liver disease is 10%. Probability that a patient is alcoholic is 5%. PAB, probability that a patient with liver disease, given he is alcoholic, is 7%. If we compute the results, as shown on the screen, you find the probability that a patient has liver disease, given that is alcoholic, is 0.04. That is as a result of Bayes' theorem on conditional probability. The economist herein would try to read more about Bayes' theorem and its present application to modern economics, especially health economics. And perhaps this could also inform the international discussion on UHC, universal health coverage, and the national health coverage, given that there are people, many citizens in this country with pre-existing conditions. The thing about insurance, especially private insurance, health insurance, that they try to insure the insurable. That is, those people who can pay, those people who can make them have profit. But a state insurance should not look at profit, but look at the well-being of everybody. We have indigents in a country. I would be really interested in one of us trying to look at SHA in light of Bayes' theorem. In this class, we talk about real issues that affect us in our daily life. Yes, we also talk about hypothetical situations, but we should also talk about real issues that matter to us as citizens of this country and as global citizens. We have UHC, then we have the National Health Insurance. If you look at it in light of Bayes' theorem, we might inform the national policy on health insurance. And we can get data from both private and public facilities. We can collect data from both inpatient and outpatient records through document analysis, having certain data agreements with facilities. I request one of you to look at SHA. I would be there to help where I can. And we make this as quantitative as possible. Because quantitative, we have replicable results and which we can corroborate. Now, there is another example of Bayes' theorem herein. in the interest of time, we look at it in class. I have one last thing to discuss. This problem is solved. You look at it at your own time because they'll be in the portal or in the e-learning platform. So for those people who are in economics and people who like jogging their minds with any kind of a teaser or a dilemma, I want you to be attentive. Now, here is another short situation, short dilemma. One morning, Mr. Black, Mr. Red, and Mr. White decided to resolve a conflict with a pistol until one of them survives. Now you see, such kind of a conflict involving two people is called a duel. However, when there are three people involved, it's called a trial. Now, those three wanted to resolve an issue, a conflict with a trial, until one of them remains standing. Now, these are their statistics. This is their data. Mr. Black is the worst shooter so far, hitting his target on an average of 1 in 3 attempts. If he attempts 3 times, the chances that he will hit once. Mr. Red is a lot better, is better. In 2 attempts, he hit the targets. In 3 attempts, he hit the target 3 times. Now, Mr. White is a sure bet. If he takes a shot, he hits it. I think I left that. Mr. White is a sure bet. 1 shot, 1 kill. Should have added that. I think it is missing. I will add it there. Now, to make the truth fair, Mr. Black is allowed to shoot first. You know, most scholars and intellectuals always side with the disadvantaged. So Mr. Black is allowed to shoot first, followed by Mr. Red, if he's still alive, followed by Mr. White, if he's still alive, and round again until one of them is alive. Now, we have a situation here. Where should Mr. Black aim the first shot? Given this dilemma. I want us to reason this out. Any hand?
Hi, Mwalimu. Let me give it a try.
Go ahead.
Yeah, I would say he shoots at Mr. White because when it gets to his chance, then there's high likelihood that he won't miss.
Mr. White, every time Mr. White takes a shot, he kills. Mr. Black, if he takes 3 shots, only one hits the target. Mr. Red, when he takes 2 shots, he takes 3 shots, 2 hits the target. So Mr. White's probability is 1/3, isn't it? Mr.
I thought you said Mr. White does not miss, meaning it could be 3/3.
Yeah, Mr. White does not miss. Mr. Black is the one that is 1/3.
Yes.
And Mr. Red is 2/3. Mr. White is 3/3. So now this is a question of game theory. Those people in economics, game theory was first developed by 2 mathematicians. One, both of them at Princeton University in the First and Second World War. One of them, John Forbes Nash, the one on whose book, with the book under biography called A Beautiful Mind. He was also a Nobel Prize winner. Then von Neumann, one of the best, most IQ persons to have walked this planet. They came up with game theory. Now we are using this probabilistically here to see what options Mr. Black has and how Mr. Black could remain the only one standing, or even transform the fight from a duel to a troll. Very good attempt. Thank you. Who else has? Hussein, can you try?
Yes, Prof.
Can you try? What should Mr. Black do in this situation?
Mr. Black will be he will, when he shoots, the probability of all of them shooting is 2, getting is 2 when they shoot equally. And I think Mr. Black will be the first one to shoot, expecting after 3 attempts, he will just get 1.
Thank you. What happens in this case, Hussein, is you take 1 shot, and then another person takes the next shot, if he's still alive. Then the next person takes the next shot, if he's still alive. Like that, until there's only 1 person standing. It is not that Mr. Black takes all the 3 shots at the same time. It's 1 shot per time at all of them. Annette, can you try?
I think in this case, Mr. Red should aim at Mr. Black should aim at Mr. White, who doesn't miss. If he misses, then if Red is given an opportunity twice, the probability of pinning him, Mr. White, is higher.
Okay, thank you for that reasoning. Now let us take this probabilistic reasoning again. Please let them to try.
So, perhaps I concur with my colleagues. So, I'm just thinking that Mr. Black, I think the best strategy is that Mr. Black can intentionally either miss the shot, but also by shooting in the air.
Well, you said he could miss the shot.
Yeah, Mr. Black intentionally missed the first shots either by shooting in the air. Then yeah, that's what that's my take.
Thank you.
If he tries either red or if he tries to shoot either red or white.
Yes.
So I'm just imagining, suppose he hit in the process of trying, then he faces a strong opponent, especially Mr. White, who never misses. Yes.
A different attempt?
Anybody else?
Yes, can I go?
Please go ahead.
So I note that Mr. Black, out of 3 attempts, only 1 would be successful.
Yes.
In the event that, and then Mr. Red, out of 3 attempts, 2 could be successful.
Yes.
So if there is an opportunity, I would say Mr. Black can donate his opportunity to Mr. Red.
Yeah.
So that Red then has would have more chances of eliminating the immediate threat, who is Mr. White, and then the rounds continue.
Okay. That's interesting. All answers are answers here. But the gentleman, that must be Ken Williams, who advised Mr. Black to shoot in the air, got the most accurate answer. And I will explain the context. First, Mr. Black shoots once, succeeds once in 3 attempts. So there's a possibility, very likelihood, 2/3 probability that he will miss that shot. And if he aimed at Mr. White, who is the strongest, and the next shot will be taken by Mr. Red, who has 2 chances out of 3, will try to eliminate him. But by shooting in the air, psychologically, he has told his 2 other competitors that, look, I come in peace, I mean well, I don't want any of you dead. After all, I'm the weakest here. So attention should not be shifting to me. Can you people sort this thing out and leave me alone? So if he shoots in the air, the next shot is being taken by Mr. Red. Mr. Red will not try to eliminate Mr. Black at all, because Mr. White, who is next, is a sure bet. So instead, he will try to eliminate Mr. White. If he succeeds, the next shot will be taken by Mr. Black, because Mr. White will be dead. That is if Mr. White is dead. However, if Mr. White is alive, he will eliminate Mr. Red, because that is the only person that has another probability of killing him. So in case Mr. White eliminates Mr. Red, in case Mr. Red eliminates Mr. White, the next shot will still be taken by Mr. Black. Now the thing will be reduced to a duel. In case Mr. White eliminates Mr. Red, the next shot will also be taken by Mr. Black, because There are now 2. But now in this circumstance, he has succeeded in reducing the fight from a duel to a duel. But now he can pray to his God or all his ancestors that the next shot he takes should try to be accurate, or is dead meat. That is the most accurate response. Now, let me tell you all other attempts that should happen should Mr. Black, the options that Mr. Black has. So let us examine Mr. Black's options. First, Mr. Black could aim at Mr. Red. If he's successful, then the next shot will be taken by Mr. White. Mr. White has only one opponent left, Mr. Black, and Mr. White is perfect shot. Mr. Black is a dead man. That is the first circumstance. The next circumstance, the next option, a better option for Mr. Black. No, let me read that option. Another option, it appears that the second option, a better option for Mr. Black is to aim at Mr. White. If he is successful, then the next shot will be taken by Mr. Red. Mr. Red hits his target only 2 times out of 3. And so there is a chance that Mr. Black will survive to fire back at Mr. Red and possibly win the duel. That is option 2. Now listen to option 3. It appears that the second option is a strategy which Mr. Black should aim in the air. That is the third option. Mr. Red has the next shot and will aim at Mr. White. Because he's a more dangerous opponent, Mr. White is a more dangerous opponent. If Mr. White survives, then he will aim at Mr. Red because he is a more dangerous opponent. By aiming in the air, Mr. Black is allowing Mr. Red to eliminate Mr. White, or vice versa. So this is Mr. Black's best strategy. Eventually, Mr. Red and Mr. White will die, and then Mr. Black will aim at whoever survives. Mr. Black has manipulated the situation so that instead of having the first shot in the duel, he has the first shot in the duel. Now, yes, go ahead.
Excuse me, Prof.
Yes, go ahead.
In the first statement of the question, the 3, you indicated that the 3 have already decided to resolve a conflict.
Yes.
Yes, so they have already decided by shooting. Then the end game is that the strongest will be left standing. I'm just wondering how stupid is Mr. White, knowing that he has a potential to kill all of them, to wait for them to kill him when he can do it once, even by double targeting. And how stupid will be the other 2 to just decide to go head on, knowing their weaknesses and their potential to die. In social science, how like someone would argue, how would this apply?
First, there are assumptions here. One, the first thing is that the shots are taken one at a time. Each person shoots once. The next person takes the next shot. It goes all around like that. It's not shooting 3 times, then you keep going. No. One shot each round. Either way, a shot has to be fired. Now, in psychology, this is about strongest than the survival for the fittest. Now, the fittest here could be fittest psychologically, since we have psychologists in this class. He has psychologically manipulated the situation to allow Mr. White and Mr. Red to eliminate each other. Then he can deal with the remaining if he's lucky. Now, I want to contextualize this. In both the First and the Second World War, let's talk about the Second World War. It was a war where all sciences were brought to bear. That is where we had the atomic bomb. That is when the US came up with the napalm, the one that was used in Vietnam, and atomic bomb used in Japan, Hiroshima and Nagasaki. The situation to be manipulated necessitated what is called deterrence. You look for a weaker opponent and beat them so bad, that then the next stronger opponent will say, no. I'm not in, I'm not more into this. So look at it this way. In the Second World War, the bombs were dropped at Nagasaki and Hiroshima. If you ignore all the other matters that happened in Pearl Bay, where Japan had sunk the ship that was meant for the US, but why look at the effect of the bomb that was in Nagasaki and Hiroshima? It shocked the world. Why couldn't it be taken to Germany, where Hitler was? And it was also a communication to Russia that, look, what we can do in future, know what we have. It was deterrence. Using game theory, probabilistically, to deter a stronger another opponent from trying to mess around. For example, today, the war going on in Ukraine, why is it that the superpower does not just go and tell the other superpower that, look, can you please leave, get out of Ukraine? Because there is what we call brinksmanship. I don't know whether this guy I want to fight has a pistol or a knife. I might go here in a fist fight and end up being shot. That kind of deterrence. So everybody is talking, oh, I have a superior weapon, but nobody wants to show that superior weapon. That is how game theory works in war, in life, and in economics. Even if you look at the situation taking place today in Burkina Faso, there's a lot of brinkmanship until Russia gets into the game. The weakest opponent here is Burkina Faso. The stronger opponents here are US, the UK, Russia, France. But the deterrence here is being provided by Russia. Look, if you mess with this guy, what we can do to you, you will regret. And you realize that in the Second World War and the First World War, certain battles and extreme weapons were used in stronger countries than those were used in Europe or America. It was a theater of war. It's a message to the strong that, look, see what we can do. If you try, we will bring this weapon to you. So that is how we have, how game theory and probability is being used elsewhere in the theater of war, in economics, in relationships, and everything else. Anybody with an observation or a question?
Yes, Prof. Mwalimu, just to comment.
Yes, please.
I think this one is now very easy. This is understandable, unlike the other ones, the figures. This is very easy.
This is, I think, is more difficult because here it is more psychological than physical, than calculatable, than computable.
Yeah, for an economist, I think it's more understandable and quite practical.
Okay. Thank you for that observation. Who else has wants to say something? Yes, please, Madam President.
Thank you. Thank you so much, Prof. My question is not on those hard mathematics, but just to refer to when you shared the course outline. I noted that for the final exam, you would put it at 40%. This is my own personal question. Is it possible to reduce the marks for the final exam and maybe to increase the marks for the group work or personal individual work so that it bears lesser marks, but the other ones bear more marks because there's more muscle being put in the group work, for instance? That's my personal question. Thank you.
Okay. All this will be weighted and we can consider that. Weighting is also a statistical tool, a quantitative tool. So we can discuss that and come to a conclusion. Because the thing here is not to pass exams, but to acquire skills to analyze your data and impact your work wherever you are. Two more comments, questions before we call off the class.
Daktari, can I comment?
Please go ahead.
I'm just looking at the policies, like the tax, so not tax, what do you call it, the tariffs was withdrawal from World Health Organization funding, and the rest which is giving countries like China who seem to have taken up. What is the end game in this, all these things, and the bullish way of diplomacy that's ongoing?
I think I lost some part of your question. Please, pardon me. Repeat the question.
Yes, I'm just saying I'm looking at the Trump policies, these are tariffs that are hitting left, right, and center, and the bullish style of doing international diplomacy, and then the pulling out of, in fact, the issue of international aid, as well as pulling out of WHO and funding, which seems to be positioning other threats to take up, like China and the rest. What is the end game if you were to apply these probabilistic theories? Thank you.
Okay, thank you. That is a question that cannot be satisfactorily covered within the time limit. But pulling out of WHO, we have what is called science diplomacy. All the technological advances that have been developed in the US and the support that has been the contribution that US has done to WHO, when they withdraw, a big gap is left. In fact, WHO already said they are having deficit in funding and urging other partners to come on board. First, US, through Trump, thinks that they are safe because they have CDC, Center for Disease Control, that is well funded. The CDC America is very well funded, and they think that they are capable of handling all biological threats, health threats in their space. If you look at the pandemic accord is an international agreement by all parties, all countries, on what to do to mitigate the next pandemics when they occur. That pandemic being handled by the international negotiating bodies is facing the following hurdles. One, technology and intellectual property. Bigger countries, more advanced like US, feel that the waiver, that they should be forced to waiver, for example, vaccine patent, to everybody will negate their business. They will not make as much money they want to make. And that has brought a lot of trouble to the negotiating body. The next being information sharing, disease pathogens sharing, like this sequencing that is being done. We know the characteristic of this disease. They also feel that the third is espionage. They think that when they release certain data regarding their technology, they would be people who spy on them and try to take advantage of such. So in the context of that, Trump thinks that they are better off by concentrating on their impact at home than giving support, technological, otherwise elsewhere. Better still, and I've done this in my book, which has a lot of quantitative, a page on quantitative, actually 2 pages only. The book is called Defeating Pandemic in the African Frontline. That if you look at the origin of pandemic, people are not in agreement on the origin of the COVID-19 pandemic. Whereas the West thinks that that China did this, who did this in a laboratory and released it as a biological weapon, there are those who believe the virus jumped naturally from the wet market into human beings as the host, and that's how it spread around the world. And that has not been resolved. So we are having another set of brinkmanship between America today and the rest of the world via Trump administration, especially when it comes to science diplomacy, technological advancement, and health and business. So in light of that, I think this is my personal opinion, that Trump administration wants to bring back US aid, but in another form that does not weigh heavily on them, having to provide too much of their resources and assistance. That is just my thought. Given the withdrawal of foreign aid via US aid, I think I also wrote an article on Standard on the same. So that is what I see. Beyond that, we can read further and understand and reason and debate. In fact, we should have a culture of debate in the university so that we're better informed, better equipped, and better prepared. That's all I can say about your question, at least in this context. We are 30 minutes, we are almost 25 minutes out of time. I think that in our next class, we will start by handling the software, where we left it, then we go to what we will do. If there is only one question.
Prof, just a small confirmation from me. As we speak, as of today, we don't have any assignment so far.
The assignments are in the, if they have not been uploaded, they will be uploaded today, all of them. And also, I'm supposed to provide you with certain data that we will be using in analysis all through and through. I will share that with the class president so that you can get access to that data, and we'll perform some analysis with it in our next class. Thank you.
Okay, Mwalimu. How are we getting ourselves into groups, Mwalimu? Should we just figure ourselves out, or will that be allocated on the platform? In the last class, they actually pre-assigned from the e-platform, so we just go in there and we find them already allocated, which might be helpful.
I think I would go with the same. We should not try to alter what is working if we can't improve it. The same way we have messed up the NHIF and the HELP and everything else. We should not change what is working if we can't improve it. I feel if it is working, we go with it. Okay, ladies and gentlemen, let's call this class off. Enjoy the rest of your weekend, and God bless you all.
God bless you too.
Thank you.
Thank you.
Thank you.
Enjoy your weekend.
Thank you.
Thank you, Prof.